In this video, we'll talk about combining functions, sums, differences, products, and quotients. So at this point, we're pretty familiar with all of the transformations that we could do with any particular function, how to move it left, right, up, down, stretch and shrink it both horizontally and vertically, as well as flipping it over the x and y axes. So now we're going to take our knowledge of functions a step further and start looking at what we can do with them when we apply different operations to pairs, trios, etc. of functions. So we'll begin with the graphical intuition behind combining functions, and then we'll do our formal definition. So consider the graphs of f and g below. F is continuous except for this one open hole there, so we know that f will be undefined there since it skips over that y value. And g is just more or less a line with a small slope. So let's add these two. Let's say what happens when we add f plus g, and we will typically write this as f plus g of x, or equivalently f of x plus g of x. So the idea is this: we're just taking a y value, an output from f, and adding it to a y value, an output from g. So we could take, we'll call this, let's look at this one, call this b. So this value here would be g of b, and that's this height, and then this one would be f of b, and that's this height from the graph of it down to the x-axis. So if we add those two values together, we're just ending up like up here. And similarly, we kind of end back up here and up here, etc. and so forth. We're just adding the heights of the two graphs. Now, when we look at what's happening here at a, x equals a, we're going to have a problem because f is undefined at that point. So the intuition would be that, okay, well, if f is undefined at that point, how do we add something that's undefined to something that is defined? So when we look at domains of functions being added together or subtracted from one another, we need to consider where a function is or is not defined. So these two look like, g might have a domain of negative infinity to infinity, and f looks like it has a domain of negative infinity, comma, a, union, a to positive infinity. So when we add f and g, we have to exclude any values that are problematic, like this one. In particular, we would write this as the intersection of the domain of f and the domain of g. So the domain of f plus g would just be the same domain as f in this case. So in summary, when we're adding, subtracting graphs, even multiplying graphs, we're just taking y values from one function and another function and multiplying them together. So whether we end up with something big or small, positive or negative, that's all we're doing. When we look at the domains of those composite functions, then we have to be a little bit more careful because we need to check the intersection of the two domains of f and g, or whatever 2, 3, etc. functions you might be doing an operation with. Let's move on. So now consider the graph of f and g below. This one I want to divide because sometimes we end up with weird things happening when we divide f of x by g of x. So f is just a horizontal line. We know that that should just be a constant, some real number. And g looks like it's just a line, but goes through 0. So now if we divide f by g, we're clearly going to have a problem at 0. So this is when we need to be careful. When we're combining functions and we're dividing one by another, and the other happens to go through 0, we need to be sure in our analysis of the domain of the combined function that we exclude any values that will be troublesome. So just for the sake of doing it, let's try to combine these functions. So we have some positive constant divided by something negative over here. So I think that will give us something negative. And as we start really negative, as we're in the direction of negative infinity, that'll be very small. And we'll get kind of bigger and bigger and bigger. And then as we get very close to 0, between -1 and 0, we'll make our combined function smaller and smaller and smaller. And then as we flip, because we're going to exclude 0, that's a problem. That's a problem for us in the domain. When we flip over 0, we start really large because we have something that's between 0 and 1. We have a fraction, a very small number, and we're dividing it into a constant. So we'll start very large, and then we get smaller and smaller as the function gets bigger and bigger. So this should look pretty familiar to you. This is just one of our irrational functions, but it's interesting to consider it from the perspective of a combination of two known functions. So in this case, the domain will be -infinity to 0, union 0 to infinity. Notice that this is not just the intersection of the domains of f and g, but it's the intersection of the domains of f and g, excluding any x values, any inputs that might create problems for the denominator of this particular combined function. So altogether we have algebra of functions. Let f and g be functions with domains a and b. Then we define f plus g, f minus g, f times g, and f divided by g as f plus g of x, same thing as f of x plus g of x, has domain a intersect b, f minus g of x, equivalently f of x minus g of x, has domain a intersect b, f times g of x, equivalently f of x times g of x, has domain a intersect b, and f over g x of x, equivalently f of x over g of x, has domain all x's in the intersection of a and b such that g of x does not equal 0. And that's the condition to make sure that we're not dividing by 0 in our combined function with the division operation.